This is Training Module 7.02a for the Stochastic Empirical Loading and Dilution Model SELDM. This training module will explain information needed for interpreting random water quality variables. This presentation has 13 slides and will take about 9 minutes. This presentation was prepared by the U.S. Geological Survey in cooperation with the Federal Highway Administration. This module has 5 learning objectives. We will learn to describe the frequency factor method, describe the skew adjustment, describe the effect of skew on the log-normal distribution, describe the detection limit issues, and describe the process for picking representative statistics. To simulate the effects of runoff on receiving water quality, we need representative statistics for the upstream and highway runoff concentrations. This schematic diagram shows a stream with a highway crossing. The upstream load for each runoff event is the product of the upstream concentration and flow. The highway load is the product of the highway concentration and runoff flow. The downstream load is the sum of the components for each event, and the downstream concentration is that load divided by the sum of flows. Both the upstream and highway runoff concentrations can be modeled as random variables. Random water quality values are defined by input statistics. If we have a mean and standard deviation, then a random frequency factor k value can be used to calculate any x value for a normal or log-normal distribution. If we have a skew value, then we can adjust the k values to produce a skew distribution. This relation is important because one way to generate random numbers in a Monte Carlo model is to generate these random k values and use the input average and standard deviation to generate individual xi values. Here's a graphical example of the random number generation process. Uniform random numbers are shown on the vertical axis and normally distributed frequency factors are shown on the horizontal axis. As the diagram shows, we start with the uniform random numbers on the vertical axis, map these numbers onto a normal distribution, which is shown as the S-shaped curve, and obtain the normal k values on the horizontal axis. As shown in the figure, the uniform variables are spaced equally on the vertical axis, but the normal function compacts values near the mean and spreads out more extreme values. We calculate the associated random concentration by using the average and standard deviation with generated normal k values as shown on the last slide. If k is greater than 0, then the concentration is greater than the average. If k is less than 0, then the concentration is less than the average. We can adjust the symmetrical frequency factor to model non-symmetrical data. We won't get into this equation except to say that the skew is S and Kn is the normal or log-normal frequency factor, which is symmetrical. This equation is known as the Wilson-Hilferty approximation and is good for skews within plus or minus 2. This frequency factor is known as the Pearson or log-Pearson frequency factor, depending on which skew you use. William Kirby developed an adjusted Wilson-Hilferty approximation, which has been approved by the USGS and is used extensively in SELDM. We won't go into it here because that method would take about 10 slides to explain. Suffice it to say that SELDM provides the methods needed to simulate positively or negatively skewed concentration variables. This graph is an example showing the effects of different skew values on simulated distributions with the same average and standard deviations. The highway runoff data and all these theoretical distributions have a mean of minus 1.05 and a standard deviation of 0.423 in log space. The vertical axis shows the total phosphorus concentrations on a log scale. The horizontal axis shows the risk for equaling or exceeding a given highway runoff concentration. The theoretical log-normal distribution is shown as the green line with a skew of 0. Theoretical log-normal distributions plot on a straight line with a logarithmic and probability axis. The pink line is the theoretical distribution of a log-Pearson distribution with a skew of minus 0.7 in log space. The gray dots are the highway runoff concentrations stochastically generated with these statistics. The simulated concentrations depart from the theoretical distribution because they are generated as a random sample and the percentiles are calculated based on the rank of the values rather than the frequency factor used to generate the values. The remaining lines show the theoretical distributions for populations with skews of plus or minus 1 and 2. The positive skews are concave up and the negative skews are concave down. the average and median of theoretical log-normal distribution are equal. However, as indicated by the bow and the lines, the median is higher than the average for the negative skew distributions and lower than the average for the positive skew distributions. In some cases, one or more highway runoff concentration values may be identified as being below one or more detection limits. In this case, the highway runoff database does detection limit statistics for you. This graph shows the hypothetical concentration on a logarithmic scale on the vertical axis and the normal variate on the horizontal axis. The highway runoff database uses the regression on order statistics method to generate the yellow line from the measured values, which are the black dots. In this method, censored values below each detection limit are evenly spaced probabilistically along the line. Then, the average, standard deviation, and skew needed to simulate the random concentrations are calculated with the measured and estimated values. We can calibrate our random statistics for highway runoff and the upstream basin by picking sites geographically. In theory, local soils and hydrology may affect runoff concentrations. This map shows the 117 highway study sites in version 1 of the highway runoff database. We continue to add additional highway runoff data in cooperation with the Federal Highway Administration and state DOTs. Version 1.1 of the highway runoff database that was published in 2019 has 242 highway sites across the country. We also have cataloged water quality data from about 330 urban runoff BMP monitoring sites and 25,000 receiving water sites across the country. We can calibrate our random statistics for highway runoff in the upstream basin by picking sites geographically. This map shows the Massachusetts highway sites in the highway runoff database. We chose sites by average annual daily traffic and ecoregion to look at variability. There were clear differences in water quality that seemed to be associated with soil chemistry in the different ecoregions. We can calibrate our random statistics for highway runoff by looking at average annual daily traffic and surrounding land uses. This graph shows relations between suspended sediment on the vertical axis, imperviousness of the surrounding land uses on the horizontal axis, and average annual daily traffic as the circle diameter. The highest sediment concentration occurred on the ultra-urban site. The two high-volume highways in less developed areas have sediment concentrations that are almost an order of magnitude lower than at the ultra-urban site. The variation of values at the relatively undeveloped sites are less clear and may depend on variables other than surrounding imperviousness or average daily traffic. Site characteristics such as average daily traffic may not quantitatively predict the average standard deviation and skew used to model random water quality. However, we can calibrate our inputs by choosing statistics from the most representative sites. This example graph shows some samples of total copper concentrations from Massachusetts highways on the vertical axis and annual average daily traffic as categories on the horizontal axis. The white triangles show the maximum and minimum. The white circles are the average. The horizontal line within the box is the median. The length of the box indicates variability and approximates the standard deviation. The symmetry of the box above and below the median indicates the skew. When modeling water quality as random variable, we want to pick a representative site. In SELDM, we may pick statistics from a few sites to see the difference. In this module, we learn that SELDM uses the average, standard deviation, and skew to generate a population of random water quality data. If the skew of the logarithms is positive, the largest concentrations may be much higher than the associated log normal values. If the skew of the logarithms is negative, the largest concentrations may be much lower than the associated log normal values. The highway runoff database does the detection limit statistics for you, and the surrounding land use and average daily traffic may identify similar sites.